Hey everybody, and welcome to this video about the slope-intercept form of a linear equation when our slope is a fraction. So let's make it happen. Alright, before we get started, here are some fraction multiplication problems, each of which involves a fraction being multiplied by an integer that are going to be really helpful for us in this section. So before we start, why don't you pause the video and take care of these 12 multiplication problems. And as you're doing them, see if you can notice any patterns arising. Alright, so now that we're done, I'm sure there are a whole bunch of patterns to find here, but the one that we're most concerned with is this. In each of these multiplication problems, we multiplied our fraction by a multiple of its denominator. And every single time, our product ended up being a nice integer. And that's a really helpful property that we're going to use in this section. So note, multiplying a fraction by a multiple of its denominator will always result in a product that is an integer. Alright, so consider this equation in slope-intercept form, y equals 3 plus 2/3 x. Now we're going to try and graph it. Now, we already know from looking at the equation that the y-intercept is going to be 3. So before we do any graphing, we already know one ordered pair, we can graph that y-intercept. Alright, now our slope is 2/3, and this is the first time we've ever had a fraction for a slope. Now, we already know what y equals 3 plus 0x looks like. That's got a y-intercept of 3, but that slope of 0 means that no matter what value x takes on, y is always going to be 3, because 0 times anything is always 0. That's why we get a horizontal line. And we already know what y equals 3 plus 1x looks like. That also has a y-intercept of 3 and a slope of 1. It kind of looks like a 45-degree line. So, y equals 2/3 x should be somewhere in between the two. Where? I'm not sure. Since 2/3 is a little bit closer to 1 than it is to 0, I don't know, maybe we'll guess around there. Alright, so we got a nice estimate of what this graph is going to look like from our graphing calculator software, but let's figure it out for sure. We already have our y-intercept, so we've got that ordered pair for free, and the slope of 2/3 tells us that for every 1 unit increase in x, there should be a 2/3 increase in y. Or for every 1 unit we go to the right on our graph, we should go 2/3 of a unit up on our graph. So in front of us, we've got this really long table of values, and this one actually goes horizontally, going from x equals -6 to +6. And then what I'd like you to do is use that slope of 2/3 and the y-intercept that we already have to fill out all of those ordered pairs. Remember, as we go to the right from our y-intercept, all we need to do is keep on adding 2/3. And as we go to the left from our y-intercept, all we need to do is keep subtracting 2/3. And in this case, you can put either mixed numbers or improper fractions. I rarely like to use mixed numbers, but in this case, I'm actually going to. So why don't you pause the video and do the same, and we'll reconvene. Alright, so we have a whole bunch of ordered pairs. Now, I'm looking at these ordered pairs, and a whole lot of them have fractions in them. And to be honest, whenever I'm graphing something by hand, I don't want to do any eyeballing. So that means I don't want to estimate 1/3 or 2/3 anytime I'm graphing. However, I do see 1, 2, 3, 4 ordered pairs, in addition to our y-intercept, that have nice integer coordinates. So let's just graph those 4 ordered pairs. And now the question is, why is it that those ordered pairs had nice integer y values, but all the other ones had fraction y values that we don't really want to graph by estimating? Well, just like we said before, anytime you multiply a fraction by a multiple of its denominator, you're going to get a nice integer. And in this case, we've got 2/3 being multiplied by x, so anytime x was a multiple of 3, we got a nice integer y value. So in general, if our line has a slope that is a fraction, using values that are multiples of the denominator for your independent variable will ensure that we obtain integer values for the dependent variable. And we like graphing integer values. So a more efficient table of values that we could have made would be to center our x values at 0, and of course that's our y-intercept, and then use x values that are only multiples of 3. To find our nice integer y values. Now I'd like to talk a little bit more about the slope of 2/3 and how it shows up on our table of values and how it shows up on our graph. So first I want to talk about our really long table of values up top. Now note that for every 1 unit increase in x, of course we had a 2/3 unit increase in y. But of course, we don't want to graph all of those ordered pairs, especially the ones with the fractions that we'd have to eyeball. Then our graph might not be that accurate. So let's look at our other table of values. Once again, our slope is 2/3. And if we look at our x and y values, for every 3 unit increase in x, we had a 2 unit increase in y. Or equivalently, every 3 units we move to the right on our graph, we move 2 units up on our graph. And now that we've found this pattern, even though we definitely have enough points to sketch our graph right now, let's go ahead and extrapolate in both directions before connecting them and drawing our line. Alright, now let's graph all of the ordered pairs for the equation w equals -3/5 k plus 4. Now right away, there's nothing wrong with this form of this equation, but I would much prefer to see this as w equals 4 minus 3/5 k, because this is how we're used to seeing it, and for me, it's much more intuitive for describing what the ordered pairs are going to look like and what the graph's going to look like. First things first, since w is by itself, let's call that our dependent variable, and so k will be our independent variable. Alright, now looking at our equation, that 4 immediately tells us that our w-intercept is going to be 4. So before we do anything else, let's go ahead and graph that point. Now the slope of this line is going to be -3/5, which means every time k goes up by 1, w will go down by 3/5. Or every time we move 1 unit to the right on our graph, we're going to move 3/5 of a unit down on our graph. But of course, we don't want to be dealing with these ordered pairs with all these fractions, and we don't want to have to eyeball these fractions when we're graphing these points too. So we want to deal with ordered pairs that involve only integer coordinates. So remember what we talked about before, I think if we use values of k that are multiples of this denominator, then we'll get values of w that are all integers too. So let's try using only multiples of 5 as our values of k. And now that we know what k values we want to use, why don't you pause the video and find the corresponding w values. Alright, now that we've got these ordered pairs, might as well graph them. Now, we're definitely in a position to graph our line now, but I still want to take some time to discuss the slope of -3/5 and talk about how that shows up in our table of values and on our graph. One more time, our slope is -3/5, and if we look at our table of values, every 5 unit increase in k resulted in a 3 unit decrease in w. Or equivalently, every time we moved 5 units to the right on our graph, we moved 3 units down on our graph. Now I hope you're beginning to see a pattern between these slopes that are fractions and how they show up in our table of values and on our graphs. Now, we have all the points that we need in order to graph this line, but of course, once we find that pattern, we can extrapolate both to the right and left to find more points. Now, I'll be honest, since we're graphing lines, we really need only 2 points in order to know what our line is going to look like. Once we find the pattern of how much our independent and dependent variables change between 2 points, we can extrapolate that pattern in both directions in order to get a good view of what this graph is going to look like and graph as accurate a graph as possible. But of course right now, we can't fit anymore because we've already gone all the way to the left and right on our axes. Might as well connect them and draw our line. Let's also find the k-intercept, and I think we're probably going to have to use the equation to do it. So we find our k-intercept to be 20/3, or as a mixed number, 6 2/3, and zooming in on our graph absolutely confirms the work that we just did with our algebra. Alright, this time let's graph all the ordered pairs for the function h of x equals 2 plus 3/4 x. Once again, this is in function notation, but the strategy is going to be no different than if we were graphing y equals 2 plus 3/4 x. So No different just because it's in function notation. All right, well, looking at the equation, first thing I see is that we know our y-intercept is going to be 2. And whenever we're graphing a line that's in slope-intercept form, I would always go ahead and just graph that intercept first. Might as well. It gives you a great baseline from which to build on. This time, our slope is positive 3/4. And this means that every time x increases by 1, h of x, or y, will increase by 3/4. Or every time we move 1 unit to the right on our graph, we'll move 3/4 of a unit up on our graph. Again, we don't want to deal with all those fractions in our ordered pairs, and we definitely don't want to have to eyeball those fractions when we're graphing ordered points on our graph. So let's use values of x that are only multiples of 4. That way we're guaranteed to get integer values for y. Now that we've identified the x values we want to use, why don't you pause the video and find the y values. Now you're welcome to use the equation to do this, but perhaps you can start anticipating what these y values are going to be given this intercept and the fact that you know the slope is 3/4. Alright, now that we have our ordered pairs, let's go ahead and graph them. Alright, we're definitely ready to graph our line, but one more time, let's talk about the slope of 3/4 and how that shows up in our table and graph. Again, our slope is 3/4, and note that every 4-unit increase in x results in a 3-unit increase in y. Equivalently, every time we move to the right 4 units on our graph, we move up 3 units on our graph. Alright, now we're ready to draw our line, and once again, let's find our x-intercept, and we might have to use the equation again to find it. So we find our x-intercept to be negative 2 2/3, which, when we zoom in on our graph, is absolutely confirmed. Now, eventually we'd like to get to the point where we can look at an equation, see the intercept, see the slope, and be able to graph it right away without using a table of values. Now, perhaps you've noticed a whole bunch of patterns with our slopes and how they show up in our table of values and graphs, and that's what we'd like to formalize right now. So, a new way to think about the slope of a line. If the slope of our line is a fraction, such as in y equals 2 plus 3/4 x, then the numerator of that fraction represents the change in the dependent variable, on the vertical axis, from its initial value, in this case it started at 2 when x was 0, and the denominator represents the change in the independent variable, on the horizontal axis, from its initial value, which is always 0. So we often say that the slope is a fraction and it represents the change in the dependent variable over the change in the independent variable. In this case, positive 3 and positive 4. Meaning our graph goes up 3 units, every 4 units we move to the right. In our previous example, w equals 4 minus 3/5 k, that fraction was negative 3 over 5. Meaning we went down 3 every 5 units we went to the right. Or in our first example, that fraction was positive 2 over 3. Meaning we went up 2 every 3 units we went to the right. Alright, time for some practice. Here we've got an equation, y equals 5 minus 3/7 x, and on the right we've got a function, p of x equals negative 2 plus 4/3 x. They're both in slope-intercept form, so why don't you pause the video and graph them. And for our last example, here's an equation that's not in slope-intercept form. So of course, let's put it in a slope-intercept form, and then it'll be much easier to graph. And why don't you try one with b being the dependent variable, and one with m being the dependent variable. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.